Going to finish up the chapter on Gibbs free energy, entropy, enthalpy, and all the other various and sundry T's that we have in this particular section. And I think I went through this yesterday, if I'm not mistaken. We talked about this slide. When you're calculating delta G, if delta G is a negative, what is the direction of the reaction?
Reverse.
It's to the left?
Reverse.
Okay. And if delta G is a positive?
Right.
Okay. You sure about that?
Yep. I'm
Have you got proof on that?
I'm positive.
I bet you're going to use the problem makes it correct.
He thinks it's positive.
Zach?
Whenever you're taking the test, are we going to have a test over these
Yes,
this chapter and the next?
We will have a test over chapter 16 and 17 after the exam.
Okay.
So sometime that next week you'll have a test over those two chapters together.
In class.
Is that the only
class.
thing that we'll have to do after that?
And then we can do more.
All right. So we got that under control. When we talk about delta G under non-standard conditions, that means we're going to vary the pressure, we're going to vary the temperature, then we're going to use this delta G equals delta G naught. That stands for standard conditions, RT times the natural log of Q. And you've already done a couple of problems like this where you calculated Q. I think one of the things that people made a mistake and they forgot when you went through equilibrium, those superscripts right there, the little b, the little a, the little d, and little c, those are the coefficients. You have to put those in when you're starting to set that Q up, or if you're setting up K or any other value, make sure you don't forget those. It's popped up several times on some of the different problems we've done so far. R is going to be the constant, 8.3145, and you have to have your temperature in Kelvin. Otherwise you will get an answer that is not even close to being correct. However, if you're taking the test, make sure you put all the stuff down, label everything. Again, they like to give you points, and they like to, there was a letter this morning in the AP chemistry teachers listserv that I look at quite a bit, and this guy in Atlanta, he posts something in there almost every single day, and they were talking about whether or not the students get points for different various and sundry things on the test, and he made a special point of saying that if you show an intent and you show, I understand this, then that's going to help you get points because they are going to give you the benefit of the doubt. But if you just simply put down an answer with absolutely no work, then they probably are just going to count it all wrong. So keep that in mind as you take the test. Okay, so here's a general trend for Gibbs free energy and equilibrium, and I have a copy of this for you that I'll pass out a little bit later on. But maybe I already gave you that one. This is a different one. Did you guys get a copy of this one? No?
Not this one.
Okay. This is a different table here. This table is in the book, though. If delta G is equal to 0, that's an equilibrium, and equilibrium is going to be, K is going to be 1, so we're doing the K here. If equilibrium, or Gibbs free energy is less than 0, that means you're going to have a negative value here. That means your K is going to have a positive value. It's going to be greater than 1. Not necessarily, it would be greater than 1. We could have a 0.1 and still have a positive value. Any questions on that? It's pretty self-explanatory. Got it? All right.
Are you going to give us that table?
Pardon me?
Were you going to give us that table?
It's in your textbook. I don't think I ran that one off. I only have one more table that I remember, and that's this one, which is coming up in a few minutes, I think, which is, maybe that's the one we've already covered that one. Oh, wait a minute.
So,
Aha! do have
Here
it.
it is. There we go.
I had the other one on top, all right, thank you, Drew. So this is one you already have, the Delta G one, right?
Yes.
All right,
Okay, I'm gonna
so
run
now
this
you
right
got it.
now.
Okay.
So, here's our old friend, anybody remember the name of that equation?
Oh.
Haber process.
Haber process, making ammonia. The history behind that thing is the guy who did it was actually trying to make the nitrates so he could make explosives in World War II, Franz Haber. So in this particular problem, delta G naught is equal to a minus 33.3 kilojoules per mole of nitrogen, and it's consumed at 25 degrees Celsius. So for each of the following mixtures of reactants and products, predict the direction in which the system will shift to reach equilibrium. So we have two different situations down here. Move that thing out of the way. Not going to do it. 1 and 2. In 1, we've got 1 atmosphere pressure for the ammonia. We've got 1.47 atmospheres pressure for the nitrogen gas, which is a reactant, and we got 1.0 times 10 to the negative second atmospheres partial pressure for the hydrogen gas. So what we're doing here is we're predicting the direction the system will shift in order to reach equilibrium. In order to solve this, you can do some quick calculations, dropping things into the formulas and coming up with something, but you've got to pay really, really close attention to the total values and the sign of your numbers. Sign of numbers is something that gives a lot of people some problems. So, with that said, find out what the values are for delta G, and then once you found out the value for delta G, the negative or positive sign will tell you the direction that that particular reaction is going to go. So let's pause the video and take time for you to